today we're going to talk about something that is, without a doubt, the bedrock of all modern electronics. It's called the MOSFET. Now, you might have heard of transistors, but this is special. It's the reason everything from your phone to your car even works the way it does.
Okay, to really get a sense of just how important this thing is, let me ask you a question. What do you think is the most common, the most manufactured item on the entire planet? Just take a second and think about it.
You might be thinking, maybe a car, or something simple like a screw or a bolt. Heck, maybe even something like a grain of rice, right? Well, nope, not even close. The real answer is way, way bigger than any of that. We're talking about something that's made in the billions. And I don't mean billions a year or even a day. We're talking billions every single second. The scale is it's almost impossible to wrap your head around.
So what is it? It's the MOSFET. That stands for metal, oxide, semiconductor, field effect transistor. I know, that sounds like a total mouthful, just a jumble of techie words. But stick with me, because by the end of this, that crazy long name is going to make perfect sense, I promise.
All right, let's dive in. We're going to start by breaking down those first three letters, MOS. See, this part of the name actually tells you exactly how the thing is built. The best way to think about it is like a tiny, super precise little sandwich.
So let's build one right now, just step by step. First, you start with a base of silicon, what we call a p-type substrate. All that p-type means is that it has a bunch of positive charges floating around in it. Then we create two little pockets inside that base that are full of negative charges. These are our n-type source and drain. After that, we lay down an incredibly thin layer of oxide, which is just a fancy word for an insulator, like glass. It doesn't let electricity pass through. And for the final touch, we put a layer of metal right on top. We call this the gate. And right there, if you just look at that little stack we just built, the name basically writes itself. You have a metal layer on top of an oxide layer on top of a semiconductor base. MOS. See? The first part of the mystery is already solved. Okay, so what about the next part? FE for field effect. This right here is where the real magic happens. Because think about it for a second. That metal gate on top, it's totally isolated from everything else by that insulating oxide layer. It's not physically connected to anything. So how in the world can it work as a switch if it doesn't touch anything? Well, you know a regular light switch, right? You flip it, and a piece of metal physically moves to touch another piece of metal, completing the circuit. A MOSFET, it's completely different. It's like telekinesis for electricity. It uses an invisible force, an electric field, that projects down from the gate and controls the electricity flowing below, all without ever touching it. It's pretty wild. So let's walk through how this works. State number 1. Nothing is happening. We have 0 volts on that gate. In this case, the MOSFET is just sitting there in its natural off state. We call this the cutoff region. There's just no way for electricity to get from the source to the drain. The switch is totally off. Okay, but now let's put some positive voltage on that gate. As soon as we do, that electric field I mentioned springs to life. It pushes down into the semiconductor and repels all the positive charges, we call them holes in electronics, basically telling them to get out of the way. And as all those positive charges run away, what's left behind? A thin little layer of negative electrons that get pulled up right underneath that oxide layer. We're starting to build a bridge. And if we keep cranking up that gate voltage, we eventually hit a magic number called the threshold voltage. The moment we hit that point, bam, that channel of electrons, it's called an inversion layer, snaps into place and connects the source all the way to the drain. We have a complete path. Now electricity can just zoom right across. The switch is officially on. And that's really the whole idea in a nutshell. We're using a metal oxide semiconductor structure to use the field effect of a gate voltage to create a switch. MOSFET. It all makes sense now, right? Okay, so we've got MOSFE down. But what about that last letter, the T for transistor? Well, it turns out this amazing little switch actually comes in a couple of different and very important flavors. So the switch we just built, that's what's called an NMOS. And there's another kind called a PMOS, which is basically its opposite twin. It's built on an N-type base instead of a P-type, and instead of using negative electrons to carry the current, it uses those positive holes we talked about. You pretty much always find these two working together as a team inside almost every microchip you can imagine. And there's just one more little detail.
The kind of MOSFET we've been talking about is called enhancement mode. Think of it as normally off. You have to apply a voltage to enhance it and turn it on. But there's another type called depletion mode, and you can probably guess. It's the exact opposite. It's normally on, and you actually have to apply a voltage to turn it off by breaking that channel.
Okay, so we've got a handle on how one single tiny switch works. That's great. But how do we go from one of these to the billions of them that are packed into your phone or your computer? Well, it all comes down to being able to precisely control a few key aspects of its design. When engineers are designing a chip, they're basically playing with a few knobs. You've got the channel length, which is the distance the electricity has to travel. Shorter is faster. Then there's channel width, which is like how wide the highway is. A wider channel can handle more current. And finally, you have to manage the substrate bias, which is just a fancy way of saying you have to make sure all these billions of switches don't start interfering with each other. Nailing those three things is the entire game of modern chip design. And that really brings us full circle, doesn't it? We now know how a single one of these things works, the most common manufactured item in human history. But it leaves you with an even bigger question, right? How on earth do you organize 50 billion of them on a piece of silicon smaller than your thumbnail and get them to work together to become the brain of a computer? Answering that, well, that's the real miracle of modern engineering.